Okay, so in this video, I would like to discuss tangent planes and smooth surfaces. So before we get into that, let's think about a derivative. So a derivative is something that measures a change in a function as the domain is changed, right? So we want to know, how does the function change as the domain varies? So if we if we think back to our derivative of f, for example, with respect to x, right? Imagine you have the function. Maybe that's not a very good example. You have, let's do an actual function. Okay, so we have this cone right here. If I think of the domain x and y over here, I draw it over there. Here is my function. This is a very stupid parameterization. What sort of parameterization is this? Well, this is x, y equals x, y, f, x, y. Yes? I mean, not technically that, but I would write r. So now I have a way to describe this surface using x and y and f, right? So if I pick a point x and a point y, I'm going to go up to f, right? And the vector will go exactly to that point, will it not? It will, and it takes in exactly two inputs, x and y. And so technically, this is a parameterization. Your book actually does give an example like this, I believe. Just go through it. Okay, so, but I don't want you to think about this particular example as a parameterization. I want you to think for a second about how derivatives work. That was the whole point. So if you don't want to think of this as a parameterization, you can just think of f, right? And then x and y. Forget about the vector form. Now, if I have some domain over here, right, and I have a value over here, this value on the domain, I could even write it down here, right? I have some square, I have some point, it's up here, right? If I move along this domain like that, or if I do it here and move along the domain, however I move, this is going to cause a move in the function. The function is going to move. And how it moves, as that movement gets really small, right, that is what we call the derivative, provided I only move with respect to x, but make it very small, using a limit definition, of course. This is going to be the derivative of f with respect to x. Okay, well, the point is this. When I do my derivative with u and v with respect to u, that little subscript means I'm taking the derivative with respect to u, then again, I simply differentiate each coordinate with respect to u. Okay, so this would be x with respect to u, y with respect to u, and z with respect to u. Okay, and similarly, I could do it with respect to v. So the question is, what does this have to do with a tangent plane? And I will now tell you. So you have some surface, and before I get into this, let's consider just a simple circle. What is the tangent line to that circle at this point? Well, if I had a function that described the motion of a ball going in a circle, right, the tangent line would just be its derivative, right? So it's going to be this thing shooting off, okay? So we all know this example from physics, basic physics. You attach a ball to a string, you spin it around, and we have this motion, and the velocity is going off, right? And what keeps the ball in? It's like centripetal, or how do they say it? Centrifugal force that keeps it in. I'm not going to talk about centripetal forces, but I do want to talk about the velocity of the ball at every point. So it's going off. Well, how do I make the tangent line? Well, the tangent line is going to be based off of that vector. So we know how to place vectors, and a line needs a point plus a vector. That's a point, that's a vector, that gives us a line. So let's think about it. A plane is not one-dimensional, it's two-dimensional. This is one-dimensional. We have a point and one vector, so we can make a line. How would I do this for a plane? It's the same thing. At every point, I can have all sorts of curves that pass through, but it's two-dimensional. So this plane, so I only need two curves. Let me say what I mean. So look at this curve I drew. At every point on this curve, I can imagine, say this is a ball, okay? A ball rolling along a hill very quickly. Maybe it's not even a hill. Maybe I threw a ball. So just forget about the hill. Just think of the line, okay? So it's really the red circle example again. So at every point, I have this this force that does this, right? This velocity, and at every point, that is the tangent line. But we don't have a line. We have a surface. So I'm just trying to kind of ease you into this. Okay, so the point is that I have this point here, and if I have two curves that go through, right? Two curves is enough to totally describe this this plane. Why? I just need to get the velocity vector from the red curve and the velocity vector from the black curve, which I'll draw green. I guess I should use a different color since that other stuff is black. So there we go. So the purple curve is the velocity vector of the red curve, and the green vector is the velocity vector of the black curve. So again, the purple vector is the velocity vector for the red curve, and the green vector is the velocity vector to the black curve. Okay? So if I had these two vectors, as long as they're linearly independent, then they can describe any point in the plane which contains them. Okay, so you can forget everything else. Just look at the green and the purple vectors, right? Just focus on those two things. They make a plane. There is a plane which contains the purple and the green vectors. Vectors, okay? Those two vectors. And what is that plane? Well, it is the plane whose normal vector is the cross product of green and purple. This is exactly how we did it in test 1, right? If we wanted to find a plane that contains, if you had 3 points and you wanted to find the plane that contains those 3 points, you compute the vector that connects those 3 points, the pair of vectors. So I have these 3 points, right? I get this vector and I get this vector, and I say that the plane, literally the board in this case, that contains these 2 vectors is going to be, it's going to contain the normal to these pair, right? And the normal tells us everything, right? Because you have a x minus x naught plus b, y minus y naught plus c times z minus z naught equals 0. Okay, well, what is the most natural thing to do, since there's all these different curves we could pick? We could do this curve, the red curve, the black curve, maybe maybe there's another curve that goes like this. You know, there's an infinite number of curves, isn't there? Right? And that's a lot of options. So why don't we make life easy? Like I always say, keep it simple. So let's just pick to vary u and v, and we'll compute the derivative with respect to u and the derivative with respect to v. And if those are the derivatives of u and v, then the tangent plane is going to be that plane which contains ru and rv, subscript v, subscript u, whose normal vector, or a normal vector, is the cross product of r, u, and rv. Very good. Now, okay, so let's think about this for a second. If I have a vector, and I claim that that vector is normal, then there's only one plane it is normal to. Well, there's a whole family of planes, right? There's this plane, right? And there's this plane, right? And there's a whole bunch of other ones, but they're all parallel. So the point is that if you have a point plus a normal, you have the plane. But if you only had a point and a vector that was no length, literally the 0 vector, you could get a whole bunch of planes that contain that, right? So, right? So if I had this point and the normal is 0, that doesn't tell us the direction, right? So I could put this plane through, I could put that plane through. Those are 2 different planes, right? Draw them like this, right? It doesn't tell us anything. So you need to have a non-zero vector, and then once you have a non-zero vector, whichever way it points, right? Like if this is a vector, then this is the plane. Okay, so that's the point that I want to make, is that this RU cross RV needs to be non-zero when I take the cross. So here's a definition you need. So we say U0 V0 is a smooth point if RU R0 V0 cross RV RU U0 V0, if this is not equal to 0. What is 0 over here? The vector, the 0 vector. So not equal to all 0. You could have 2 of them be 0, and the third one be non-zero, but it has to be non-zero. So why is it called smooth? Well, there's a motivation for it. Okay, we're pretty much done with this video, but let me give a reason, and then we'll be done. And one more thing. If every point on your surface is a smooth point, then we say that the surface is smooth. Let me write that. So the surface is smooth if every point is smooth. Okay, so So a point is smooth if at that point the cross product is non-zero and the whole surface is smooth if every point is smooth. That makes sense. So let me explain why this makes sense. Okay, so it's a very stupid example. So here's our absolute value function x. I'm just going to keep it in the one-dimensional case. Okay, so if I try to compute the derivative, we know the derivative does not exist. So here's the plot of the derivative, right? It's going to be -1 on the right, +1 on the, -1 on the left, +1 on the right, and at the origin, the derivative does not exist because they don't match up. So we don't say that this is smooth because it has a kink. It has a little point right there. So you might ask, if I had to ask what is the tangent line at this point, what is it? Well, it's that line, isn't it? So at this point, I have this tangent line, right? It's just the line. And I can keep going, and I can do it here. But you might ask, what is the tangent line at that point? What is it? Well, it doesn't exist, again, because the tangent line is the unique line when we say the, right? And if it's from this side, it'll be like this, and from this side, it'd be like this. And so they fight, and neither one of them wins. And so there isn't a unique line that describes the tangent space. And it would turn out that if you tried to compute the normal vector to the tangent plane, it would just be 0. Okay? So I'll see you in the next video. We'll do some examples.